All right, folks. Good morning or afternoon or whatever time it is. Again, new month, new year, new sick child. I will be back on Wednesday is my goal. So hopefully everything goes well there. Just a little head cold with the kiddo, but a fever. So the first part of this video is actually going to be me catching up. So if you are in first or second period, you can actually skip ahead a couple minutes. I have a specific set of problems to do with sixth period that I want to do first. So if you skip forward about 3 to 5 minutes, that should get you where you want to be for the next problem. With that said, we had left off in sixth period right here with consider this function, and we talked about above and below. Now I didn't get a chance to really discuss this portion with y'all because we had to take that formative today. But what we should have realized, the big point here that I want to bring up, and if you could just jot down this note, is we talked about this idea that area was 8, but the integral was -8. And what I really want you to realize is that area is always positive. Integrals are both positive or negative. Okay? Areas are similar. Area and integral are similar, not the same. We calculate them mathematically the same way. If I say the area of a triangle, 1/2 base times height, if I say the integral and it looks like a triangle, we still do the 1/2 base times height, but the integral can go into that negative. So that's this part down here, and that's going to be a really important differentiation. I'm going to give you questions where I'm going to tell you that I have some area, and I'm going to tell you, hey, the area below this curve is 9 and 12, and you have to recognize that if the area is 9 and 12 underneath the curve, then between the curve and the x-axis, but the curve is below the x-axis, you have to recognize that that area, even though this right here has an area of 9, that means that the integral for that area is actually -9. And you've got to catch those little weird nuances of language as we go through. So we get through that, we talk about this. We also have to deal with the idea of what happens if I have a function that not only stays above or below the x-axis, but we're going to have functions that curve underneath. And I'm going to ask you to find the area between two endpoints such that we have an area above the x-axis as well as an area below the x-axis. So what happens when we get a situation like this where we've got two different pieces? And the idea here really becomes we really just find the area of this upper piece, and then we go ahead and we find the area of the lower piece. You realize I'm using the word area, so I'm talking about these positive numbers. And all I'm going to do is I'm going to take the area above and the area below and just do a subtraction piece. The area below becomes negative. The area above becomes positive. So if I were to give you, say, some particular graph, I don't know, looks kind of freaky. And I've got some B, and I've got some A, and I tell you that the area above the x-axis is A1 and the area below the x-axis is A2. And I ask you to find the integral from A to B of f of x dx. Then essentially what I need to recognize is that I'm going to take the area 1, and I'm going to subtract from that A2. And that's all that means. I just take the pieces above and below the x-axis and move on. Fairly straightforward question. So if I were to break this into a piece that's something that we haven't looked at, I could look at this question. What I'll let you do is I'll let you pause the video, and I just want you to take a shot at this. Pause the video, try it out. Draw the function 1 minus x between the endpoints of 0 and 3, and see if you can evaluate that limit will be. Or what the integral will be, not a limit, sorry. All right, so what you were looking at is you should have had a pair of coordinate axes And we've got the graph of 1 minus x. So we've got a y-intercept of 1, crosses the x-axis at 1, and then at 3, we go down to, I hope that's right. Oops. Apparently that'll be negative 2. There we go. So make sure that my picture looks good here. Oof. Come on now. There we go. There's my negative 2. And if I take the integral of this between a and b, what we're really looking at is we're really looking at two separate regions. We have a region right here made above the y-axis, above the x-axis, as well as a region below here. So this spot right here is going to have an area. Let me use a different color here. There we go. This will have an area that will equal 1/2 its base times its height, its base being 1 and its height being 1, has an area of 1/2. This piece has an area of 1/2 its base, which is 2, times its height, which is 2. So we have an area of 2. So if I'm taking, and now I want to point out, again, what am I using? I'm using the word area, but when I solve the integral, I can take that area above the x-axis minus the area below the x-axis, and you'll see that I get a negative value, which shouldn't surprise us because clearly there is more area below the x-axis than there is area above the x-axis. We should get a negative number, and you can do that. You can eyeball those things and see those things to your advantage. All right, for the rest of us, this is where everybody else has stopped. So welcome back, first and second period, unless you decided to watch that little piece. Glad for you to join us here as we talk about the next section. As you can figure, we're going to see some trig. We are going to join the Church of Math for just a moment here. I'm going to state a fact, and I'm going to hope that you believe me and trust me that I'm not going to lie to you too much, at least at this point in time, unless you take upper level math and you find out that, you know, there are obviously some simplicities that we point out in some places. Not too many, though. But I'm going to tell you that it is fact that the integral from 0 to pi of sine of x dx is 2. And that is a 100% true statement. I'm not messing with you. It is simply 2. It seems weird that that can be 2, but we'll just go with it. With that information, we're going to be able to figure some stuff out. We're going to be able to figure out all 8 of these integrals with just our knowledge of sine. So what I want to do is I want to, what I would like to do is I would like to take this and draw a sine function real quick. Oh, I don't want to do it in that color. So I'm going to draw a sine function. It's a long sine function. All right, I know that the important numbers for sine are 1 and -1. I know that I need to go through the point 0. I know that 0 is also important. I also know that the most important problem points that I want are going to be pi and 2 pi, as well as pi over 2 and 3 pi over 2. And if I have these 0, pi over 2, pi, 3 pi over 2, and 2 pi, I have got myself I can graph sine and cosine with enough accuracy that I am good to go. And I'm going to draw this so I know I've got the point 0, 0. I know I've got a point at pi halves that sine is equal to 1. At pi, sine is equal to 0. At 3 pi halves, sine is equal to -1. And at 2 pi, sine is equal to 0 again. It helps if I actually hit my dots. Close enough. And what I told you in the problem previously is that the integral from 0 to pi, this region right here, is equal to 2. If you haven't figured it out yet, the main piece of this problem is going to be utilizing symmetry to our advantage. So, for instance, I take a look at the first question, and the question simply asks, what's the integral from pi to 2 pi? So I look from pi to 2 pi, and I see that it's the same exact shape. except that it is now below the x-axis. So if the area above this is 2, then the area below this will also be 2, but because it's below the x-axis, we say that the integral is -2. If I ask you what is the integral from 0 to 2 pi, well, I know the area above is 2. I know that the area below is also equal to 2. So if I go from 0 to pi, that's +2, but from pi to 2 pi is -2. This becomes 2 minus 2, and we say that the net integral is 0, which is interesting. Areas of 0 are typically not important to us, but these become really useful. This tells us, if I'm dealing with displacement, this tells me that I've moved out, but I also moved back the same distance. So we can use some information there. If I want to look at the integral from 0 to pi halves, I simply realize that that is exactly, realize my graph is not very symmetric at all, but I realize that that is exactly half of my 2. And as you would expect, since this graph has got so much symmetry within it, this is simply going to be whatever this answer was, but half of it. So we have an integral that equals 1. Now I've done all of this without any cool calculations. I've done no antiderivatives, which are going to be the fancy thing we're going to do later down the road. I have not done anything with a calculator. I haven't done anything strange. Just with my base knowledge of what the integral from 0 to pi is for sine of x dx, I have already answered 3 questions with very little thought. Now it's going to feel like that changes with 4, and I'm actually going to come back to 4 here in just a minute. I'm actually going to do a couple of the other problems first, and then we're going to go from there. So I'm going to save 4, and I'm going to save 6 for the end. I want to look at 5. So 5 says 2 sine of x dx from 0 to pi. And what I want to point out then is if we're thinking about how this works, the graph of that means that every single one of these points is exactly 2 times its original height. So, you know, instead of it being at 1, we're up here at 2. Instead of this being at like 1/2 here, this is actually at 1. So when I draw this graph, it really does some cool stuff. Now I have not multiplied the width by anything, but I've always multiplied every single height by 2. And this is way back in an old school 8th grade math topic, back for most of you 7th grade, some of you 8th grade. But when we multiply a dimension, a height or a width, remember that if we break these into a bunch of rectangles, all we've done is multiplied a bunch of heights by 2. So what we've done is we've doubled the area. So we say that this has an area equal to, oops, not 2, but 2 times 2, and we say that this has an area of 4. I'm going to give you a minute to try out 7 and 8. Before we get to 4 and 6, those are the weird ones, I'm going to give you a minute to try out 7 and 8. So if you've paused the video, hopefully there, and you tried out 7 and 8, I am going to go ahead and do those now. So on number 7, we're taking the sine from -pi to pi of the sine of x. So I go back to my graph. I don't have a -pi, so I'm going to have to go back to that. Okay, well, that's kind of annoying. Let's go back to -pi. So my knowledge of functions is good. We know that that's -pi over 2. I've got to go back to -pi. So if I do that, this should be -1, kind of following the pattern, back up to 0. So this kind of does something like that. But wait, this region is the same thing as this region. So if I go from -pi to pi, I start with a area of -2, or an area of 2, right? We would say that this right here would have an area of -2, and then we'd add to it a +2, and we would say that we would have a net integral of 0 once again. Likewise on number 8, if we did a cosine graph, let me just scoot over to this and I'll do a real quick cosine graph, 0 to pi, so I only have to go out to pi. Pi halves, we start at 1, we go to 0, and then we go down to -1, and it looks something. Whoa, helps if I actually go through the dot. There we go. Now, one of the things I want to point out, I have not told you what the integral of cosine is, but some of you may have actually already figured it out, because we know that sine and cosine are pretty much the exact same curves, which means you should actually already know what this little section is, because this little section matches the section that we just solved a second ago when we did from 0 to pi halves. Well, so I take a look at this and I go, well, this is something. Maybe I don't know what it is. Maybe I have no clue what this is, but I understand how integrals work, and I understand that cosine and sine have some really cool symmetry. If I go from 0 to pi, I've got a piece above and a piece below, and because of the symmetry of cosine, we know that those are the same points, just above and below the x-axis. So we can say that that also has a net area of 0. Again, we've done no work. I didn't have to know anything about cosine and sine other than what it looked like. And even then, that was a little weak. So, what about 4 and 6? Let's talk about those real quick. So let's draw number 4. 4 was a sine graph, but it was the sine of x plus 2. So that's weird. Sine of x plus 2. So I still have all of my normal points. I've got a pi. I've got a 2 pi. I've got a 3 pi halves. I've got a pi halves. Got everything that I would normally want. But I want to graph the sine of x plus 2. So that means that I don't actually start at 0. Sine would mean sine of x plus 2. So when I do plug in a 0, I would go all the way up to 2. And then when I go to pi, that would increase by 1. So that would go up to 3. And then pi would bring me back down to 0. And then 3 pi halves would take me down to -1. Oops. Yep. And then pi brings me up to here. And we have a graph that looks something like that. This is the sine of x plus 2. Again, I didn't catch the symmetry of this quite as well as I would have liked to. Clearly my pi is significantly larger than my 2 pi. But we do know that there is symmetry, so we can work with that. It's 2 plus sine, but whatever. Same concept. And I want to know what on earth is going on from 0 to pi. So I really don't even need any of this piece. I just need to worry about this. I'm looking in there. Well, what do we know? What do we know about this thing? Oh man, sine plus 2. So what I want to look at is I want to realize if this were just sine, we would have had an x-axis right here, right? And we know what this region in blue, we know what that region is. This region in blue, that has an area equal to 2. That's what we said earlier. There's just a vertical shift, so that just means we're here. So when I look at this, what I really want to recognize is that there is this other shape that it's on top of, though. It's just a rectangle. And from geometry, most of you got really good at composite figures. What do? We find the area of the two pieces that we do know, and when we put them together, we get the area of a shape that we don't know. This piece right here, this is just a rectangle. How large is the base for this rectangle? Well, the area would be the base. The base in this case is pi, and the height would be 2. So this has an area of 2 pi. And if I want to find the area of this entire shape, we simply take the 2 pi plus the 2, and we say that our answer is 2 pi plus 2. It's that easy. If I want to take the integral of this, oh my gosh, what is this? The sine of x minus 2. Here we go. Here we go. Sine of x minus 2. This is where things get kind of nasty. So let's talk about that. Sine of x minus 2 is going to be the same exact graph that we're used to seeing, except it's going to be shifted to the right. So instead of going through at 0, 0, it's going to go through at 0, 0 at 2. And instead of maxing out at pi halves, it's going to max out at pi halves plus 2. And instead of hitting 0 again at pi, it hits 0 at pi plus 2. And then we got 3 pi plus 2 and all of that. Not that I think I need those data points. So take a look. And for those of you who are going, huh, what's going on? We go like this. And if we look, pi is like right about me. Pi halves, where's pi halves at? Tell you what I'm going to do real quick is I'm actually going to put up a nice graph so you can see what I'm actually trying to show you as opposed to me trying to draw this in. So we're going to bring over our good buddy Desmos here. And we're going to take a look at that. So I want to just kind of show you. We've got the sine of x, and we've got the sine of x minus 2, which we should know is a horizontal shift. Bam! So if we had changed the limits, we could see that really this graph is the same exact graph, it's just that every single point is shifted over exactly 2 units. Cool. What does that tell us? Well, that tells us that now we're trying to find the integral of this particular weird and ugly looking thing. And I want to find the integral at 2n pi plus 2, which if I went from 0 to pi, 0 shifted 2 to the right is just 2. And pi shifted 2 to the right is just pi plus 2. So sometimes you'll get questions where the limits of integration are shifted the same exact way and the same exact amount as the original function. And we find out that the answer has been under our nose all along. It's 2. All right, with that said, one more set of things I want to look at. The last skill and one of the biggest skills, you are going to be quizzed on this during a formative, is this last one, the ability to draw a graph and be able to pull the area from that. So what I mean by that is if I look at this first question, I'm going to draw a graph of 4x. So I put my coordinate axes up. I draw the graph of 4x from 0 to b. Where is b? Don't know. Let's call that b. And if that's b, then this point has to be 4b, because if I plug a b into that function, it's 4b. And I want to find the area of the region that is created here. So the area of the region created here, okay, b is clearly not that far over. Here's b. And if I go and I look, what we're really looking at is the area between the curve and the x-axis, so it's that region I just shaded. So when I look at this integral, I can say the integral from 0 to b of 4x dx is equal to the base distant, 1/2 the base, which is b, times the height, which is 4b. And we get an answer of 2b squared. We wash our hands and we walk away. I'm going to give you a moment to try out numbers 3 and 2. Go ahead and pause the video and give yourself a shot. All right, if you didn't get a chance to pause the video, you can go ahead and do that now, but I'm going to go ahead and I'm going to start both of these questions. So again, just like any other problem, I've got the graph y is equal to x. So I'm going to go ahead, I'm going to graph y is equal to x. It's a good graph. And I'm going to graph this, but now I'm not going to be between 0 and b. I'm going to go between a and the square root of a. So I've got a here, and I've got the root of 3a. And I've got this shape. I want to know what the area of that shape is between the curve in the x-axis. And so what I want to do is I want to realize that this shape, well, what is that? That is a trapezoid. So the integral from a to the square root of 3a of x dx is the average of the bases, a plus the root 3 of a over 2 times a height, which is the square root of 3 of a minus a. Now that's the part that probably messes with people, but if I'm looking for distance, we just take the remember that distance is the largest value minus the smallest. So when I'm talking about how far apart the endpoints are, we just take the final minus the initial. Another way to think about it. And then we would multiply this through. So I would say we've got a times 3 root a. I'm going to factor out that 1/2. I'm going to have the root 3a times a, but then I'm going to get a negative of that, so that cancels. So this really turns out to be 3a squared, this times this, and then a times negative a is minus a squared. And 3a squared minus a squared is just 2a, and half of 2a is just a squared. And we walk away happy people. All right, last but not least, folks, we are almost there. We got one last graph. We've got 3t. We're going between a and b. So again, I'm going to draw my axes. I'm going to draw my, hey, not cool. I'm going to draw my curve. I'm going to go between a, and I'm going to go between b, which means this is 3a, and this is 3b, and I'm looking at this region right there. Again, we've got ourselves another trapezoid. So this integral from a to b of 3t dt is going to be this particular integral, a trapezoid. So this is the average of the bases, 3a plus 3b over 2, times the distance between these bases, b minus a. I can factor out a 3 over 2 in this problem. Call this a plus b times a minus b, which is 3/2 of a squared minus b squared. Or sorry, this is b minus a, not a minus b. So that's b squared minus a squared. And we're done. Ladies and gentlemen, the biggest things I want you to take away from this, if there's anything from this lesson that you pull from it, it's that drawing the picture is going to be useful. The picture will show us what type of shape we're dealing with. You are going to need to be able to recognize your shapes. The big ones, triangles, rectangles, trapezoids, and eventually into like quarter circles, semicircles, not really usually circles, although that could happen. If you know your area formulas for those things, and you can figure that out, otherwise, like the problems we did for sine and cosine, if you can play with symmetry, you've got the problem beat. You've got the rest of the period, which isn't a huge amount of time, but you have the rest of the period to work out more problems that are based on this. I'll take questions tomorrow about these, and I hope that everything goes well. So, like I said, I plan on seeing you on Wednesday. I do apologize for my not being here, but I'm the one who's kind of got to use the days right now. So I hope everybody has a good day, and I look forward to seeing you soon.